Osipov, and today I'm going to present Picodata. It's a shard per core in-memory database. This talk is available online. You can visit it at my GitHub. So it's at Kostya GitHub.io. There I write some technical articles. You might also find them interesting. So a few words about Picodata, like what this talk is about, whether or not you still need SQL databases and memory databases, what you need them for, where Picodata is good at, and basically it's mostly about technical ideas that I find fascinating and you might also find interesting. So what's shard per core and why shard per core is important and where, like how you classify all of the databases and what's the place of Picodata in this hierarchy on this universe. Yes, the shard storage, shard memory, shard nothing databases. The advantage of shared nothing databases is obviously that there's no shared state, so they are massively concurrent, massively parallel, and they scale because there is no single point of failure, no single point, single bottleneck. And the idea of shared nothing databases is that all the data is sharded from the beginning. And Picodata implements this. Basically, it's think about it this way. If you have to shard, then let's shard based on CPU cores, not on nodes, not on computers, but every CPU core is a shard. And with Picodata, every CPU core owns a partition of data exclusively. It's an independent process, and different processes communicate with each other. I'll show you how. So how do others like compare, and whether or not this is some kind of a unique trend or not? It's not. If you look at the modern applications, the design of modern high-performance applications, most of them use asynchronous I/O and shard per core patterns. And yeah, like Rust, Discord, Scala, Red Panda, in C++, C Star framework. So Picodata also implements high performance message bus between cores and uses it. And as I said, the data, there is no concurrency, there is no contention for data because all the transactions, they run cooperatively in a single thread and they own a single partition. So single thread transactions are very fast. From the distributed point of view, the cluster, Picodata cluster itself, it's a distributed, highly available cluster. So it's every core has a peer somewhere in a different data center. We call these data centers failure domains because it doesn't have to be a data center. You can implement a replicated cluster within a single data center. Then your failure domains are going to be your racks or your even computers, and you can even use virtual machines as well, so to implement high availability. So the way it assembles is that every instance, it has a peer replica or multiple replicas. So there is a leader and a follower in every replica set. And as you can see in these three data center clusters, they're like the leaders are evenly distributed between data centers. So DC1 has a leader, DC2 has a leader, DC3 has a leader, and two followers in adjacent DCs. The idea is that the cluster fully assembles itself, fully manages itself, and you only need to add and remove nodes from the cluster. Now, this is like physical layout, and there's also logical layout. So the data within replica sets is also logically sharded, and that's a different kind of sharding, like another layer. And it's a bucket-based sharding. And the reason we need buckets is that it allows us to very like easily, without significant overhead, to redistribute data between replica sets. So replica sets usually for in-memory database, they are about 20, 30, 50 gigabytes inside. in a single bucket is of data, and in a single bucket is maybe 30 or 50 megabytes. I'm sorry. So every replica set holds a bunch of buckets. By default, there's 3,000 buckets per replica set, but you can increase it. There is not much overhead. There's no need, but for a large cluster, you can easily have 300,000 buckets and so on. So whenever we need to rebalance data, because for example, you add a new replica set, we just first of all, these are independent processes. You add a replica set to a cluster and it joins, it's online, it can serve queries, but it doesn't have to own the data. And this allows you to quickly add multiple replica sets, quickly scale the cluster from compute point of view. And then asynchronously in the background, we rebalance concurrently buckets from other replica sets to it. So in this illustration, you can see that RS2 and RS1, they concurrently stream their buckets to RS3. And so the data is rebalanced already after the replica set is online. Next thing I wanted to talk about, one of the key ideas, is that the data distribution. So most NoSQL databases generally and horizontally scalable databases, they are built on top of a key value store. And the problem with that is that it is difficult to preserve data locality if you have a key value store. Of course, if you have NoSQL workloads, key value workloads, then a single key is your object, is your domain, and for relational workloads and for joins, for analytical workloads, you actually want to decompose complex domains into a relational schema. So naturally here in this example, I use TPCC schema from TPCC benchmark, from TPC consortium. And what it allows you to do is to pick, what Picodata allows you to do is to pick a thing called distribution key or keys. So in every table, you can pick columns which are used for data distribution across replicas and across buckets. And this ensures that collocated data, that essentially connected data, stays together, it's local, and you can join locally. So you can push down some OLTP, OLAP joins to specific instances, and they execute without any data movements at all. The other technique we use to increase data locality is a thing called global tables. So some dictionaries, some small tables that change slowly, you can replicate to every single node. This also makes joins with these tables very fast because they don't need to jump to other nodes. And here, like we in this illustration, we use this combined method to maximize locality and maximize throughput of the database. So in TPCC, warehouse table is a small table. It contains the list of all warehouses, and item table is also fairly small, about 100,000 items. It contains the inventory, the product catalog, so these are replicated identically across all of the replica sets. And then for every warehouse, we have a single replica set that serves it. So whenever we perform transactions against this warehouse, it just goes to a single instance. And this allows us to achieve a massive scale of the database. So the more warehouses you have, the more cores you can potentially utilize for your database. So that's another key idea. Another thing we implement in Picodata is a thing called failure domains and tiers. So the tiers allow us to kind of map topologies into failure domains. The idea is this. Every instance it's like the closest thing to compare it with would be probably table spaces, because it's the tiers and failure domain together represent some kind of a physical locality and physical resource. So a tier is a logical division, a logical attribute of every instance. And here in this illustration, for example, you have a hot tier, a cold tier, a compute tier, and an arbiter tier. Why do you need all these? So for every tier, you can independently define its replication factor, its storage type. So hot storage is in-memory storage, cold storage is LSM tree, like in Cassandra, or like in, I don't know, RocksDB. So, I mean, you can have exclusively cold storage, a single tier in your database as well, or any other. But the idea here is to illustrate a complex application that has in-memory tables and hot storage. Replication factor for those is 2. Cold tables like archive and cold storage, again with replication factor 1 already, and some compute nodes, again with replication factor 1. And arbiter tier, it doesn't have any buckets, so you independently define the number of buckets for every tier. So by defining 0 buckets for arbiter tier, you can say, hey, this tier cannot store any data at all. And here, the arbiter tier is the only tier that is replicated in 3 data centers. And so Picodata, it actually has 2 replication rings. One ring is global, it includes all nodes in the cluster. And another ring is per replica set. So every replica set has its own replication, and every replica participates in the global replication. So what we do here with an arbiter tier is we delegate cluster management to dedicated instances in the cluster, which have increased availability. So they are represented in 3 failure domains. And this ensures that the entire cluster stays operational even if DC1 or DC2 goes down. So this single node in DC3 guarantees that the majority in cluster management is always present, even if DC2 or DC1, DC2 or DC3 are down. So the raft ring actually stores the schema, the access control, the bucket map, the topology, and every node sees this, has an identical copy of this information. So every node has the full information about which nodes are up, which are down, which are present in the cluster, which are removed from the cluster, what are the privileges, and so on. But the data is distributed across domains and tiers. So let me speak about the UX a bit. So how do you assemble such a cluster? We spent some time thinking about it, and as I said in the beginning, the idea is that you minimize the you want to minimize the friction with the DBA when you assemble nodes and when you manage such a cluster. So Picodata implements only 2 operations from cluster management point of view. That's the joining, and you just do Picodata run and specify one of the peers here to join the cluster. And init replication factor defines usually you specify these things in the configuration file, but it defines the replication factor of a new cluster, and it's not necessary to set it up for joining nodes. So mainly for joining nodes, you need to specify the peer and the failure domain to show where the node resides, so that the cluster manager can effectively create replica sets and repair degraded replica sets with joining nodes and so on. So, if you want to kind of replace a node or extend the cluster and fix the cluster, whatever, you just use expel. So expel, you specify a UUID, and actually there is a comment here that why don't you, every instance has a name, also a very short name, useful. We assign it automatically, you can assign it yourself, but to expel you need to specify instance UUID, and this is just a safety net so that you never expel the same instance twice, because every instance UUID is unique, obviously. So to sum this up, Picodata implements a distributed SQL database. It has primary storage, which is a memory database, and has secondary storage, which is cold. You can specify a replication factor to ensure availability and redundancy of your data. You can, the replication is synchronous, and the disk writes can also be set synchronous. So the transaction manager within the cluster is serializable. It's limited to a single shard, but it's serializable. And the tiers are a way to separate compute, storage layers, and scale clusters independently. So here I prepared a short demo to show how the cluster could be like assembled. I'll just play it. So here we create a cluster with replication factor 3 and 3 replicas. And here is some neat part. We actually use PostgreSQL API to connect to the cluster. So you can connect to using PGWire protocol, PSQL client. And generally, the SQL is PostgreSQL compatible. I'll speak about this in a second. One thing to pay attention to that here in this demo, we first granted the privileges to the test user and then connected with this test user. So when you install a database from scratch, it obviously doesn't have any users except the system users like guest and admin. And you need to create a user to connect or grant set password for admin user. And then we have a special Unix socket file where you can connect as admin and set the password. So let me speak a bit about PostgreSQL compatibility. We implement all of the core features of PostgreSQL SQL syntax, all of the core data types, plus some of the analytical functions like window functions. We do implement joins, unions, group by, and so on. And also, the important aspect of the management is that we implement alter system here to set up and configure the system. So basically, the idea is that, which is which is not true oftentimes, that in some of the NoSQL products, is that like you should be able to do everything using SQL basically, except the topology itself, except adding and removing the nodes. There's a huge advantage in being part of the PostgreSQL ecosystem, because many tools, they just connect to Picodata and then can work with Picodata, and that's very neat. As an enterprise, so a couple of words about our business model, how we actually make money. Picodata is open source. It's distributed under BSD license, but we do have enterprise offerings. And in enterprise, we ship extras. So one of the extras is something like XDCR replication, and it allows you to set up logical replication between independent clusters. And now I want to talk about something completely different, and that's plugins. So why plugins, and why is it something completely different, and why is it related to in-memory databases? One way to look at the database is that it's like a container for your data, but your logic for the data is still in the application server in some backend application. The problem with this approach is that the time to access the data is increased, and there is a network, and network is a bottleneck. So for memory databases, for really high performance workloads, you do want to have an ability to put the logic of your application inside the database as some kind of a stored procedure. And we implement support for that using plugins. Plugins are written in Rust, and Picodata is written in Rust as well. And they are executed in the address space of the instance of the database process, and they have instant access to all of the data. And since there are no transaction logs, there is just transactions run in using cooperative multitasking. This is really, microsecond speed, not milliseconds. So if not nanosecond in some cases. So we implement a full life cycle of plugins to allow to install, upgrade, enable and disable, and configure plugins in the cluster using SQL. So the separation of concerns is that it's similar to PostgreSQL extensions, but these are cluster-wide extensions, and we guarantee that extensions work with each other. So you can have multiple plugins because we do actually care about plugin compatibility and plugin management from SQL. So the manifest is a file that describes the plugin, essentially binary object tarball, and it shows it's used during installation. So the first step is to ship the plugin to all of the nodes as as a tarball or as an RPM package or whatever. The second, you just configure and enable it from SQL, and these are separate steps so that you can first verify that it has successfully installed on all of the instances. Then you can configure it and ensure the configuration is identical at all of the nodes. And the third step is you can actually migrate between versions, and migrations are SQL commands, which allow you to, when you upgrade the plugin to the new version, you can upgrade the schema as well, upgrade the data to match the new version of the plugin. So we take care of that. So where is it useful, and what's next? We are in the standard sort of ballpark of in-memory databases, e-commerce, ad tech, like telecom, career grade applications in the telecom, real-time tariffs in banking, in any kind of billing. So any high throughput OLTP is our niche, and plugins help very much because whenever the performance is not enough, we can create a plugin which would do just the thing for the client and essentially speed things up a bit more. We are also working hard on improving our SQL support. So think about this as an analytical storage as well. If you are ready to put your data in memory, and your analytics is mostly per client, and you can massively scale this analytics. And OLTP database with row-based, not column-based storage format is good for you. With that, I invite you to reach out, join our Discord. We have a Telegram channel, and you can just reach out to me if you have any questions or need help. Thank you.